Hi, this is an example problem from Chapter 13 on heat conduction via radiation. Pause for a moment and read the question. So in this case, we've got a couple of stars with different temperatures. They have the same radius, and we're going to try to figure out what is the ratio of total power output of star Y to that of star X. We're told that the emissivity is script E equals 1.0. Let's go ahead and look at the equation that describes radiative heat transfer. So Q divided by T, the heat transferred per unit time, also which we call the power, given by this equation where sigma is just the constant here, Stefan Boltzmann constant. E, this emissivity script E, is a indication of how reflective the surface is. If it's reflective completely, it's 0. If it's a perfect absorber or emitter of radiation, it's 1. And the star we saw is 1 here. The area of the star, now for a star, that would be a circular surface area, so the area of a sphere. And the temperature T to the 4th power, important that you always use for T Kelvin. Let's go ahead and write this equation down. So the power radiated, the heat per unit time is equal to sigma script E, surface area of the radiator, times the absolute temperature to the 4th power. Now we've got two stars in this case. We've got star X and star Y. So let's go ahead and see what information for this equation, for these parameters, these quantities in the equation, we can figure out for these various stars. So first thing is we know the temperatures, right? So star X is the cooler one. It's got a temperature of 5,727 Celsius, right? So we got to convert this to Kelvin, we're going to have to go ahead and add on a certain amount here. 273 degrees, right? Is going to convert this into Kelvin. So the temperature of star X actually, well, this one was made obviously to add 273, comes out to 6,000 Kelvin. Important that we convert that to Kelvin. Now the temperature of star Y, that one is 11,727 Kelvin. Again, add 273. Turns out this one's going to be 12,000 degrees Kelvin. All right, let's see. Both stars have the same radius, right? So the area of X is going to be pi rx squared. Well, since the radius is the same, that's going to be the same value for star Y, right? And finally, both stars can be considered to have an emissivity of 1, so E is the same for both, and sigma, of course, is just a constant, same for both. Let's take a ratio of these two. Total power of star Y as a ratio to that of star X. So the power of Y as a ratio, power of Y to power of X. We're going to go ahead and write in the equations. And in fact, I know the area is the same. I don't really need to write that. Sigma, epsilon are the same for each. It's only the temperatures that are different. So all the stuff that's the same in the numerator and the denominator, we can cancel out. Sigma, epsilon's both 1, areas are the same, and we are just left with the ratio of the two temperatures to the 4th power, the absolute temperatures. Now, since these are items that are squared and they're divided, we can go ahead and do this to simplify a little bit. Now, since we've already have the temperatures in Kelvin, we can go ahead and directly plug those right in. And we know that the Kelvins will cancel, so we can ignore those if we want. 12,000 Kelvin for star Y, 6,000 Kelvin for star X to the 4th power. Well, that's going to be 2 on the inside to the 4th power. And 2 to the 4th power is 16. So we see that the ratio here of star Y to star X is a factor of 16. Star Y is emitting 16 times the power of star X. It's only twice the absolute temperature, but because of the dependency on temperature to the fourth power, it produces a big difference in the amount of heat radiated.